Longitudinally structured light is light that is designed to change certain properties, like wavelength and orbital angular momentum, as it propagates through space. Light needs to follow Maxwell's equations, which govern its electric and magnetic field components. The scalar wave equation, which I discussed in a previous video, can be derived from Maxwell's equations in free space. Much like how we solved the wave equation, we can define an error functional where S is our desired optical field and E is the closest we can get while obeying Maxwell's equations. We then create an adjoint function lambda and solve this fourth-order differential equation to find it. Once we've found lambda, we plug it into this equation to find the field that most closely matches our desired result. Similar to the setup in the previous video, the boundary conditions of the field are plugged into a spatial light modulator as a hologram, and a 4F system is used to filter and demagnify the optical field. This setup also includes polarizers and inhomogeneous media for the light to propagate through, both of which we will explore soon. One of the advantages of longitudinally structured beams is their ability to reconstruct themselves after interacting with obstacles. On the left here, we can see a longitudinally structured beam encountering two walls that combine to block line of sight in the x direction. Our beam is able to mostly reconstruct itself after the walls, in contrast to the Gaussian beam on the right, which is destroyed by the interaction. And here we see how beams interact with a dielectric wall, shown here in red, that imposes a phase shift of 135 degrees on part of the beam. The left image shows a longitudinally structured beam that is able to keep its shape past the wall, while on the right we see a Bessel beam, which is typically able to self-heal, but in this case is split into two major parts. In a previous video, we showed the ability of longitudinally structured light to follow curved paths through homogeneous media, but just as impressive is how it can follow linear paths in inhomogeneous media. As an example, a beam is passed through a material whose index of refraction varies linearly in the y direction. On the left here is a Gaussian beam, which is bent and dissipated by the optical gradient. On the right, however, our structured beam is able to follow a straight path, as well as keep a consistent intensity at its center the entire way through. An advantage of using Maxwell's equations to control the electric and magnetic field vectors of beams is that it gives you control over the polarization of light. A beam was designed that, after propagating a certain distance in air, splits into two parts, each with polarization orthogonal to the other. This mimics the effect of a tool called a polarization beam splitter. The left column in these photos shows the overall pattern as the beam passes through space and splits. The middle and right columns show the optical field as seen through a vertical and a horizontal analyzer, respectively, which each only allow light polarized in that direction to pass through. As you can see, spot A consists of just vertically polarized light, and spot B consists of just horizontally polarized light. In addition to working with beams of light, these techniques can also be applied to create and manipulate more intricate optical structures, like two-dimensional planes of light. And we can alter these planes in much the same ways we did the beams. Here is the 3D structure of a light sheet that twists in midair. Looking at the transverse intensity profiles at different points, we can see the sheet starts off flat, but becomes diagonal at quite a steep angle after only 12 centimeters. For another example, here is a light sheet that bends as it propagates. There is a noticeable difference in shape at the end of its path compared to the beginning. And lastly, we can design a sheet that splits in two at a certain point. This sheet may remind you of the four-way beam splitter that was demonstrated in the last video. A type of light sheet imaging called light sheet fluorescence microscopy is used in biology to image microscopic samples while minimizing light scattering and phototoxicity. Longitudinally structured light has potential applications in this and many other areas of imaging and optical microscopy. I have included some relevant papers for your convenience. Thank you for your time.